Okay, something that we've touched on with SF4, if you remember, was the idea of an expanded octet, something that is known as hypervalent or hypervalence. Okay, this was, if you remember, where the sulfur, instead of being all happy with 8 electrons, had to have those extra 2 electrons, so now it has 10 electrons, right? Miserable, blah, blah, blah. Okay, this happens because of the electronegativity of fluorine. So you see these hypervalent type species where you have fluorine, to a slightly lesser extent oxygen, to a slightly lesser extent chlorine, and so on. Because fluorine is so electronegative, it goes up to the sulfur and it says, "Oh, give me some electrons. I don't care if it makes you unhappy. I'm going to bond with you. You haven't got anything to say about it, or else I will beat you up on the atomic scale." Fluorine really is a nasty atomic bully. Okay, so SF4, you got a sulfur with those 2 extra electrons, if you like. Okay, one way to think about it is, of course, sulfur starts with 6 valence electrons, 4 fluorines, use up 4 of them, it's got 2 left, which of course means that you could even imagine another sulfur fluoride, SF6, in which those little electrons have been used up by 2 more fluorines, and indeed SF6 exists. It's actually rather a fun little gas. It's a very stable, very dense gas, and you could use it to talk very, very low, but it's a bit sort of dangerous, so you really shouldn't do it too much. Okay, anyway, then we can have other ones. PF5, right? 5 things. Look at that phosphorus, it's got 10 valence electrons around it. You can have interhalogen compounds, right? IF5, that iodine has got 2, 4, 6, 8, 10, 12 around it. Okay, and indeed a lot of these hypervalent species will be fun ones in the next big section we'll talk about, which is where we are predicting the shape of molecules. Okay, now one of the lovely parts of this, and I'm being a little bit revisionist history wise with this, but bear with it because it's not too bad, is that this idea that fluorine can make atoms do what they otherwise really wouldn't want to do has led to the emergence of the field of noble gas compounds. If you take a noble gas and you react it with fluorine, some with oxygen and so on, you can make compounds, and one of the classic ones of this is xenon tetrafluoride. Okay, xenon, happy little noble gas, but 4 fluorines come up, beat the poop out of it, and take its electrons. Okay, make it share their electrons with them. How would we draw this Lewis structure? Well, obviously it doesn't follow common sense, so we'll step 1 count the valence electrons. Xenon has 8, right? Unfortunately you got to count it as 8 rather than 0. 4 fluorines, 7 each, 28, total of 36 valence electrons. Obviously xenon goes in the middle, add in the dots, and when you put the bonds and then you say, well, the xenon, poor little xenon, is going to be drawn happy with its 4 bonds here, and then each fluorine has got the 3 lone pairs, so there we are. Trouble is that's only 32 dots, so what you got to do, you got to add 2 more dots on the 2 more lone pairs, excuse me, on the xenon to give you that structure. Okay, hypervalence is where you have central atoms. They've got to be at least 3rd period atoms, if you remember, central atoms that have more than the 8 electrons. Now, this ability of some species to go hypervalent has had, as well as being intrinsically interesting for chemists, it's brought in some things that I think are rather disgusting and hideous as a perversion of the Lewis model. Okay, and that is, and this is I'm sure how a lot of you learned to draw some of these structures in high school, that is where you just arbitrarily and without the slightest concern draw Lewis structures that have hypervalent atoms when they don't need to be hypervalent. We had no choice in those last ones but to draw the sulfurs and the phosphorus and the iodine and the xenon as hypervalent. There were too many electrons not to do so. Okay, but there is a big debate, and it ranges still today in high school chemistry books and general chemistry books. Most real chemists don't give a crap about it, but we got to kind of talk about it anyway. Okay, as to what is the correct way to draw Lewis structures for some of these species. Okay, and the problem comes up with these formal charge twits. Okay, formal charge is a silly little tool that sometimes, like we did with the N2O, can help us decide on what the best Lewis structure is for something. But formal charge has got absolutely zero physical meaning. Okay, but you have some people who love the idea of formal charge, who say that you cannot draw things that have huge formal charge separation, even if it means you've got to violate the octet rule. Now, from my personal point of view, the octet rule is one of the central themes of chemistry. You do not break it lightly. Okay, but you have these formal charge people who argue, but formal charge is so much more important. So I'm just going to throw a few examples out at you now, and you'll be able to apply the idea to some of the ones that you've done in school. Okay, SO2, we drew it like this. Everything happy. Okay, no common sense at all. And of course the formal charges were 0, 1 and -1 as we worked out. The formal charge people would draw it like this with 2 double bonds. Now look at that sulfur and count its electrons. It's got 10. Why you would be so stupid as to put 10 electrons when you can draw a structure quite feasibly with 8 electrons, I don't know. But the way they argue it is here the formal charge is yucky, 0, 1, -1. If you assign formal charges here, you will find that in every case they are 0. Okay, octet rule, beautiful, wonderful thing, or crappy old formal charge. Okay, another one would be perchlorate. When you draw it our way, you get this chlorine at the middle of 4 bonds to oxygen. Okay, however, some people draw it like that. Count up what that poor little chlorine's having to go through, right? 14 electrons. Okay, formal charge argument, well, if you believe in formal charges, it's pretty significant. That chlorine's +3 and each of the oxygens -1. Never mind, of course, the fact that your formal charge people would say, well, oxygen wants to be -1. In this case, they're like, no. Let's just have that -1 oxygen there and everything else will be 0. Okay, again, octet rule or formal charge. Another fun one is BF3. Okay, if you draw it our way, right, then you get this. It obviously has resonance, right, because you've got the choice of where you're going to put this double bond. So it's actually just like nitrate. The bond order is 4/3. Or you get the people who say you don't need to do that, you can just draw it like this. Trouble is though, now you're blowing the octet rule in the other direction. Now you're making something that is electron deficient. Formal charges really don't look that hideous for us. And in the formal charge camp, they're all 0. Now, these electron deficient molecules, and we'll talk about one of these again in a little bit more. BF3, obviously, when it reacts, it is behaving like it wants more electrons. It's a very reactive species. So the formal charge people say, well, it's because you need these extra 2 electrons and the boron. Don't have a problem with that. What we argue, though, is that you can actually get to the octet rule by making the fluorine double bond. Now, obviously, fluorine don't want a double bond, so therefore this thing is still going to be reactive in order to make the fluorine happy. Okay, octet rule versus violation of the octet rule. As far as we're concerned in this class, it is still a debate. It is still ambiguous. Depending upon whom you listen to, you can find people who say there's experimental evidence for the octet rule version, there's experimental evidence for the formal charge version. The truth is you can argue the experimental evidence both ways. Okay. What we're going to do in this class is we are going to say that the octet rule is paramount. If you can obey the octet rule, that's what you're going to do. Okay, but I do want you aware that there are a lot of times 2 ways to draw Lewis structures. It is because it is a simplistic theory. Reality, as we saw with resonance, is undoubtedly between these extremes. Okay, but for this class, this is the goodie. This sucks. Okay. Now, I mentioned with BF3 the idea of electron deficient. Molecule in which an atom just doesn't have enough electrons. Okay, and that's another example of a weird, screwed up type of Lewis structure. So other messed up Lewis structures. Well, there's 3 types of messed up Lewis structures. The first type we've already addressed, where you have too many electrons, you have an expanded octet, hypervalent, SF4, SF6, PF5, IF5, XeF4, and so on and so on and so on. Genuine expanded octet, not these made up ones like these formal charge twits do, but ones where there is no choice. There's too many electrons to fit them in any other way but saying one of these atoms is forced to have more than 8 valence electrons. And there's probably, I don't know, I'm throwing out a number here, 80, 100, 120 known stable molecules that are hypervalent like that, okay, at least with the main group type elements. Now, if too many electrons is one type of messed up Lewis structure, too few electrons is another type. These are electron deficient, and these are truly electron deficient. These are species in which you can't get the octet rule, okay. Two great examples of this. The most classic is BH3, boron trihydride. Added up, boron, 3 valence electrons, hydrogen 1, so you got 3 plus 3 ones is 6. That is the Lewis structure. There is no choice of that. BH3 does all kind of weird things in order to get happy that are beyond the scope of this course. By the way, it is worth mentioning that boron is weird. Boron is in group 3. As it's in group 3, you would say, well, it was surely easier for it to lose 3 electrons than to go up to 8 valence electrons. And the answer is yes, it should be, but boron is a metalloid. Only metals lose electrons. So therefore, boron can't make B3+. Boron has to try to get up to 8. And so it does all kind of weird things, right? But one thing you can always say is boron never follows common sense. And in this case here, boron can't even get up to the octet rule. Another one that I hesitate to put down there because it's weird, and this is only true in the gas phase, is beryllium hydride. Okay, now you'd look at this, you'd say beryllium, surely it is ionic because beryllium is an alkaline earth metal. Beryllium is actually, yes, it's a metal, but it's a very weeny metal. It has a lot of properties that are more in common with a metalloid, at least in terms of how it behaves chemically. And BeH2, BeCl2, and so on in the gas phase are covalent molecules. And again, if you add this up, Be's only got 2 valence electrons, 2 hydrogens. There's only 4 valence electrons here. Okay? So, too many electrons, one type of messed up Lewis structure. Too few electrons, another type. The last type are odd numbers of electrons. There are a few species that exist that don't lose or gain electrons immediately, right, as one would expect if you've got something weird, but they just sit there with their odd number of electrons. These are given a name. These are called free radicals. Okay, radical is you've got that unpaired electron, right? An electron that's neither paired in a bond nor paired in a lone pair. There's two classic examples of this are both nitrogen oxides. Okay, NO first of all. Add up, valence electrons, 5 for nitrogen, 6 for oxygen, 11. Connectivity, no choice but the nitrogen bonded to the oxygen, so we throw in our dots and we get this, which has 14 dots. Okay, so obviously we've got to reduce that. Well, we can go down to 12 fairly easily. We just remove a lone pair from each of these atoms, add a bond, boom, there's 12 dots. Okay, but now, screwed. We can't do it again because that would give us 10 dots. We want 11 dots. So what we have to do is we just have to erase a dot from one of these atoms. Which atom would you say? I would trust you would guess that it will be the nitrogen, seeing as how oxygen is more electronegative. So erase a dot from the poor little nitrogen. There you go, 11 dots. Free radical. That nitrogen is very, very, very reactive. A lot of times you will see NO not as a neutral molecule, although it can go in, it can cause ravaging to your body, for example, to biological systems looking for that electron, right? It actually wants to act as a oxidizing agent because it wants to gain an electron there quite a bit. Another word for an oxidizing agent is an oxidant, which is why a lot of times you worry about taking antioxidants that are going to suck up any free radicals like this. You'll see NO plus when it loses that and makes a triple bond. You'll see NO minus when it gains an electron there. Okay, but NO does actually exist. It's rather yucky stuff. Another one that you guys actually made in lab, nitrogen dioxide, if you did that copper with nitric acid lab. Okay, add it up, 17 valence electrons. Nitrogen less electronegative, so it goes in the middle of the two oxygens, put in the normal bonds, and you get 20 dots. Okay, we can certainly take those 20 dots down to 18 dots by removing lone pair from here, lone pair from here, adding this. Of course, those of you following will realize this is one of those things that can exist as resonance. I could have put the double bond there. But again, now we've got 18 dots. We can only lose one more to get down to 17. We will remove it from the nitrogen. And so we end up with this picture with 17 dots. Nitrogen dioxide, very nasty substance indeed. Dissolves in water to give you nitric acid. That's why if you breathe it too much, your lungs will rot away. And of course, you're much more familiar when you see NO2, not with NO2, but with NO2 minus, where it has gained an electron to become the nitrite anion. Okay. Now you are absolutely world experts on Lewis structures. The next thing is using Vespa to go from Lewis structures to predicting the shape of a species. But I very much doubt that you'll get to that PowerPoint for at least 24 hours. Make sure you are really good at drawing Lewis structures before you come to that.